Hello, my friends of Hatari Labs. Welcome to this tutorial. This tutorial will be about groundwater flow simulation at mine closure time scale with MODFLOW and model Muse. So what is this about with this complicated name? Okay. In this tutorial, we will focus on how to simulate groundwater flow at very long time scales as the related time scales to mine closure. So we will be talking about 50 years, we will be talking about flow simulation at 80 years, and most importantly is something about the chicken and the egg. So we will analyze which is the time scale of at mine closure with this with the result from this flow simulation. Okay, so in our philosophy of the tutorials, we do not want to make a tutorial for the whole set. I mean, this tutorial won't be related to the construction of the model. The model is actually already constructed on steady states. Yeah, so we will change it to transient flow conditions. Okay. And this tutorial will be more related that you understand what is the result, how is the relevance of the storage when we have achieved the steady state conditions after close, and in the end when we will have achieved closure in the end. Okay, so this is mostly the purpose of this tutorial. You are invited to follow the other tutorials. Please do not expect a tutorial that will cover everything, because in order to build this, maybe you will require 8 hours of tutorial. So nobody's right now. But if you want to drop some ideas about future courses on groundwater modeling, please, you're invited to. Okay, so you will receive this file, that this will be groundwater modeling my closure bus 1. And this file is, if we go to MODFLOW time, is in steady state. So we are going to build a model on closure. Okay, so which will be, and this will be the mine closure of a tailings storage facility. Only this, because there is another topic about mine closure of open pit, and another topic is mine closure of waste dam. Okay, so we have here here we have the tailings storage facility. So if you see here, so maybe you would like to see the hydraulic conductivities to see the different materials. Okay, this is the tailings, this is the dam, and the alluvial aquifer, and the upper, middle, and lower fractured aquifer. Okay, great. What else? Okay, first of all, we have to define the mine closure transient stress period. Okay, so what we will do, I will go to layer groups, no, to time, and then I will apply another stress period, but this one will be transient. This will be transient, it's already transient, and we will run a simulation of maybe 80 years divided by in every on time steps of 4 years. So let's do the 80 years. Actually, I will work on seconds, because you have to be consistent that seconds is the only time unit of the whole model. Okay, so I want to say I want years to seconds. Why not? And then say 80 years is actually this number in seconds. Copy to the clipboard, then close, and then here I can paste it. Okay, great, that's great. And then here on the length, no, here on max first time step length, I can say that, so if I want to simulate 80 years every 4 years, I will have 20 time steps. So 20 time steps is this one. Okay, okay, great. That will be fine. let's say, okay. Okay, so how is mine closure? Imagine that you will close the tailings storage facility. And how do you close the tailings storage facility? Is that actually you put a cover, I mean, you put a geomembrane or like a soil cover, everything that you are entitled to do and what your budget will do. Okay, so then, and how this soil cover or like geomembrane cover, mixed cover also, will affect the groundwater flow conditions. Actually, the only thing that will be related to the cover of this tailings storage facility is that recharge will be reduced. Okay, but as you will know in this tutorial, that recharge is reduced is not, I mean, do not imply that the whole tailings storage facility won't is isolated from the groundwater flow. And this is something that we want to discuss here. Okay, so the tailings storage facility is in fact related to the groundwater flow, even though recharge is not applied due to the implementation of a soil cover. Okay, so if we first of all, we have to define when you do a closure or like a transient a transient simulation, you have to update your boundary conditions. Okay, so first we have to update all the boundary conditions, and then the latest boundary condition to be updated will be recharged on the tailings storage facility. Okay, so here we go to drainage. So I go to this one, and flow, it won't be on the steady state, it will be till the end. Okay, then I go to here, and then this will be till the end. And then CHD, this will be till the end. And evapotranspiration, these ones will be till the end. And actually, this one is recharged, but this is recharged in the whole model, and the whole recharge on the whole model is like this. But however, we have recharge on the tailings. Okay, so recharge on the tailings, this won't be till the end, because then we will insert a time and a stress period from 0 till the end, and here recharge, let's assume actually even that you apply a geomembrane or even that you apply a good soil cover, you cannot imply that the cover will be 100% effective in time. Okay, remember, we are dealing with time, we are dealing with a scale, with a time scale of years or decades. Okay, so in this case we are going to imply that actually after you have closed the tailings storage facility, there is no recharge on the system. Okay, but we are not sure, as a scientist, we are not really sure about that this will happen, but okay, let's see. So here we have -1, 0, and from 0, and then the recharge rate after closure is 0. Okay, that's right. Cool. So then we save it, and then I will save it as bus 2, because in bus 2 is actually with these changes. So bus 1 is actually without any change, and bus 2 is with those changes. Okay, cool. Then let's have a, well, what we have done, we have inserted a stress period, and the second is that we have updated our boundary conditions. Later on, let's see which are our some budgets. Okay, So let's go to here to color grid, and then I go to here zones. Okay, and then here we have 101 is the tailings, 0 is by default, and then we have here this is 201, but let's see that by default is 301. Okay, so 101 is the Tailings Storage Facility, 201 is this channel, and actually this channel is actually where water will be seeping from the tailings dam. There is another tutorial that you are invited to see. Okay, and then let's see on data. The data set by default is 301. Yeah, this is very powerful for the analysis. Okay, so 101, 201, and 301. Let's save. Okay, and then please run it. Okay, you run it. We will run. Okay. For all the people that want to learn groundwater flow modeling, I really invite you that you follow the tutorials, and I really invite you that you follow the tutorial, actually that you look at the whole tutorial, yeah, then you try to reproduce what we show you, and then understand what the data that you got from the model, that you get from the model, and then try again, and then try again, and then try again, understand well, and so on, and then maybe change one thing, or maybe a minor thing, and then maybe change another thing, and then really start with your own project, okay? Because on my years of practice on groundwater flow modeling, many people, most of the people want to do a model for their own case, okay, or their own model. But if you don't have the expertise in dealing with the software, with the convergences, with the package and so on, then this doing something, a groundwater modeling from scratch, and then do not understand what you have done is really hard. It really implies the quality of your work, really. So if you want to do something good, something that actually is useful for making decisions, you have to increase your capabilities. Okay, that's why most people, most of the people do groundwater flow modeling, but actually they see that this is not so easy as doing hydrological modeling, and then they drop. Okay, we see that because actually in Spanish we gave many courses on groundwater flow modeling, and the number of people the number of students that come from the beginner class is like 6 times the number of people, the number of students that come from the intermediate. Okay, cool. So then we have the simulation. Okay, then I'm going to close. If you see in this is the water budget, and the water budget this is for the steady state, and this is from the transient. Okay, 80 years every 4 years. Okay, and then here we see the okay, then this is the water balance. Okay, this is at the end is storage in is actually water that comes from it's related to the depression of the water table or the hydraulic head. So when the depression of when the water gets lower, actually you will have a storage in. Yep. And when you have a rise on the water heads on the water table, you will have a storage out. So if you compare the storage in with the storage out, you will have, well, it's not so much, it's 0.3 liters per second, because actually this is cubic meters per second. So I do the conversion on my speech. Okay, so it's low, constant head, that means the regional flow actually give 69 liters per second to the system. And the recharge that is do not occur on the tailings storage facility is 93 liters per second. Okay. So from this, the regional flow takes 58 liters per second. The drainage to the system, to the whole drainage system is 86, and then 18 liters per second that goes into the wetlands. Okay, cool. Okay, let's see, and I will show you which is the water table at the beginning of closure, and then which is it's not even the beginning of closure. It's the beginning of closure and then after 50 years. Okay, so here I will open the BHD or the FHD. It really depends if you are working with binary and so on. So I will do at the beginning and then at the end, and neither, because I will be only interested in the water table. Okay, there are many, this model is not so light, so there are many layers. Okay, I suppose it's importing those. Okay, cool. And then we are going to, let's see. Okay, cool. Let's say here in cross sections, data, optional, more results, water table. And here, this is the first one, and this is the latest one. On the first one, and this is the dark blue is the first one, and light blue is the second one. Well, actually, it's not light blue, it's more like a turquoise. But let's see. Okay, close. Cool. Look, this is the water table. This is water table at the beginning of the simulation, and this is how it has dropped at the end of the simulation. But, okay, maybe I will show you the contour. After 80 years, there is a drop of just 5 meters in the water table, yeah, according to the hydraulic parameters on this case. And if you see, I will show the contour data for the end. For the end. Wait. I don't like this color scheme because it's light blue to dark. And here I will show you the songs. Just to have a better. Okay, that's great. Or maybe the key. Yep. Okay, that's great. Okay, what do we have here? Let's take it out. This. Okay. Do you see that this is the initial groundwater, the initial water table, and this is the final water table after 80 years? If we apply RC, we can see that there is an inflow of the groundwater flow here at the beginning, on the upper part of the tailings storage facility, and there is an outflow here in the lower part of this. This inflow and outflow have not changed so much on closure. Okay, so this actually water that on the original setup was draining to the water channels, but actually they are draining to the tailings storage facility, because actually the tailings storage facility is located in the lower part of the basin of the elevation. Yep. There is an inflow there and there is an outflow. This inflow and outflow that perseveres or that lasts for many decades actually is not good. Is something that is not good for the environment, because if you see, the water that is coming in will be highly affected by the leachate and the lixiviation from minerals of the tailings. Okay, so that's why we have to take this into account when we design mine closure. Okay, because if you don't take this into account, the efforts that you put and the money that you put on your closure schemes will be, I mean, won't be worth it. Okay, because in the long time you will have more problems. I mean, then we will see we will see that actually, okay, this water here will be, I mean, um, the implementation of this land cover over a tailings storage facility, yeah, will drop or will decrease the inflows to this channel, yep, to this, okay, but it won't, it will decrease, but it won't stop, okay. And if it will decrease and it won't stop, actually you will have leachates from the tailings storage facility coming out on this part, yeah, and this will imply on a time scheme of maybe 100 years, 200 years or so, and this will imply a remediation scheme, okay, an active remediation scheme that most probably won't be run by the mine company. It will be run by um, by the governments and so on. So what do we do? And okay, there is, as an engineer, we have to make a solution for this, but for the to start, we have to understand how this is working. Okay, so in order to see which are the inflows to this water channel, or the discharge from this tailings storage facility to the water channel, we go to we will use a small software that is groundwater chart that is you will find on the USGS website. Okay, chart type, we go to water budgets and then file, open. Okay, great, and then I go to one here. Okay, here it is the set B list. Okay, and actually it requires a this, but it's in the same place. Okay, cool. Okay, so 101 is the tailings storage facility. Okay, cool. And but okay, in and out. I want to show you the 201 drains. Okay, at the beginning of this, I mean at the closure, this section of the water channel of the stream network was draining 34 liters per second. Okay, by the implementation of this mine closure, okay, of this mine closure or this soil cover, or it is, or maybe the soil cover, or maybe the by the implementation of the soil cover, you have dropped this only on 10%. Okay, because in the end you have 31 liters per second, and mostly since you have this interaction in between the 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 tailings storage facilities, this water will be highly affected on their quality. Okay, we can run a particle transport with a transport model with MT3D, yeah, the new package of the USGS, but this is something like a summary of what will happen, okay? Because remember that the transport model is actually coupled to the flow model. We will have problems, okay? And then we will have problems, and this kind of simulation is key for the evaluation and the simulation, for the evaluation and the analysis of the feasibility of the closure schemas. Okay, so this is mostly the tutorial that I want that I wanted to give this day today, and I hope that you have found a really good example and it's really applied. Yeah, we are passionate from modeling. That's why we do not that we wanted to show as applied as possible. Okay, let me want to present our blog. Our blog, it is Hatari Labs. It's a blog on open source software in groundwater modeling and GIS. Okay, we have we have many tutorials on MODFLOW with model Muse in QIS and so on. And we hope that you can follow us, that you can share our posts on your social networks, and then maybe you can subscribe to our newsletter, because we will be publishing and making some good tutorials and applied tutorials as well. My name is Saul Montoya. It was an excellent pleasure to have you, and see you in another tutorial. Bye bye.